Now, I actually showed you the universal wave equation yesterday near the end of class when we were talking about this spot here in town, okay, where the speed limit changes, right, from 100 kilometers per hour, okay, to 60 kilometers per hour. We were talking about how the frequency of cars passing an observer here and here is the same, because the frequency of a wave cannot be changed once the wave is produced. Okay? Frequency is a property of waves that never changes. Right? Once the wave is produced, its frequency cannot change. Right? Evidence of this is things like sound. Again, I think I talked to you about like hearing sound above water and hearing sound below water. You hear the same sound. I mean, obviously it sounds a little garbled, but the tone, which has to do with the wave's frequency, is the same whether you're in the water or out of the water. Okay? Because once the waves enter the water, both their wavelength and speed will change, okay, as a result of entering a new medium. So the universal wave equation looks like this. V equals F times lambda. Since we know that frequency cannot change, if speed changes, wavelength must change as well in order to maintain the frequency. Everybody follow my logic there? Yeah? So if my if my speed gets cut in half, how much smaller does my wavelength get? Same amount. If I'm going to keep the frequency the same, okay, V over lambda always has to equal the same number. So if V gets half as small, well, so does lambda. They have to decrease by the same amount in order to maintain the frequency of a wave. Okay? Another example with the whole waves going from air to water could be light. Okay? Light's an example of a transverse wave, but its frequency doesn't change either. Okay? If I'm above the water looking at a green light and I go down below the water, I still see green. Okay? The color of light has to do with its frequency. Frequency doesn't change. Everybody follow there? All right, and so yeah, we talked about how out here, right, the cars would be this far apart, but so their wavelength would be a certain number. They're traveling at 100 kilometers per hour. We reduce their speed down to 60 kilometers per hour. Their wavelength has to decrease, or the spacing between them has to decrease, so that I still see the same number of cars going by me every second. All right? Everybody good with that? All right. So, does that equation look like it's very difficult to use? No. It's V equals d over t for waves. And I'm not kidding when I say that. That's actually what it is. Okay? I mean, V equals, right, like we got wavelength, okay, and we got 1 over time. Okay? So this is actually distance over time. Because it can also be written like this. Wavelength over period, right? Because t is 1 over f. So it really is V equals d over t. The length of a wave divided by the period of the wave is distance over time. It's meters per second. Okay, now that said, there can still be some tricks. They're contextual tricks, not math tricks. They're contextual tricks, okay, that have to do with universal wave equation problems. So they're just things you have to be mindful of when you're reading the questions to do with universal wave equation, rather than, oh my gosh, I'm going to have this incredibly complex mathematical computation to do. No. V equals d over t. It's not a complex mathematical computation for you to do. All right, so what can affect the speed of a wave is going to be kind of the key point of today, okay? And then learning to use the universal wave equation to solve universal wave equation problems will be the next thing, and then that'll lead us into tomorrow, which will be about interference, what happens when waves occupy the same space at the same time, which will lead us into wave behavior, which is what happens when a wave goes from one material to another. That's kind of, today is kind of the introduction to that mathematically. Thursday will be more contextual, okay? Friday, standing waves. Monday, standing waves. Tuesday, kind of finishing up. Wednesday, finishing up. Okay, Doppler effect, okay, that kind of stuff, and then we'll be done. All right. Yesterday, when we were watching those videos, and they were talking about waves coming into shore, okay, they said the waves slow down and the wavelength gets shorter as the waves approach the shore. And the reason for that was the properties of the medium change. The medium the waves are traveling in is water. The property of the water that's changing is depth, how much water there is. If there's suddenly less water and it's less deep, the waves are going to slow down because there's less medium to transmit them or for them to travel through. So their speed decreases. So what affects the speed of a wave, very simply, is the medium in which the wave is traveling. All media convey waves or transmit waves at different speeds. Sound and light are the two best examples of this. Right? If you were a jeweler, for example, okay, you would take advantage of this idea. So you might not know this, but stones are cut in certain shapes. Okay, we cut stones in certain shapes to make them sparkle. A raw diamond is not all that pretty. Okay, when they pull diamonds out of the ground, they look kind of like quartz. They're just kind of a clear rock. Right? They have to be cut in order to sparkle. The reason that they sparkle is because as light enters them, it slows down. And when you slow any wave down, you can change the direction in which it travels. So the idea with a diamond or any other stone is that if you get light to come in, you want it to slow down and change direction. If you cut a stone the right way, you'll cause it to have what we call total internal reflection. That is, that as the light comes in and gets bent and changes direction, it'll hit another facet. That's a face or a cut on the stone. If the angle is right, that is this angle down here, the light will not escape. It will reflect instead. It'll go over to another facet. If it's cut right, it'll reflect. And it'll come back out the top, causing it to sparkle. Okay? So we take advantage of the fact that waves travel at different speeds in different materials in order to cut stones. Incidentally, this is also how they can tell the difference between a cubic zirconia and a real diamond. Right? An experienced jeweler takes 5 seconds to tell the difference. All he does is looks at this angle at the bottom of the stone. Okay? That angle is specific to whatever material the diamond or the stone is made out of. Okay? So if it's a ruby, it would have a certain angle. If it's a diamond, it'll have a certain angle. If it's glass, it can have a bigger angle. Okay? That's all they have to look at. They'll know right away. Guys, they'll know right away. Okay? Life lesson. I didn't have to learn this one. I was smart enough on this one. Okay. She's worth proposing to. She's worth the real diamond. Just keep that in mind. And they always find out. Okay? So, all right. Don't take any chances. But yeah, like I say, it takes like 5 seconds for a jeweler to know whether that thing is real or fake. Okay? And that's 5 seconds for you to get in the biggest trouble of your life, probably. Right? So spend the money. Questions?
No, I was just saying, when you started talking about your wife, I thought you were actually talking about the law, like the law that gets the ring.
Oh.
So it just caught me off guard that you said about your wife instead of the actual enforcement, because the experienced jewelers that can find out first.
Oh yeah, experienced jewelers can find out right away. Yeah, absolutely, and they'll do it quick. But yeah, spend the money. She's worth it. All right, so it'll come back out the top. Depending on the material, the light bends differently, okay, because it slows down more or less. Diamond slows down light more than any other material. So light bends the most in a diamond, so it can be cut quite narrow, right? Something like glass that doesn't slow the light down nearly as much as diamond has to be cut a lot wider in order for this total internal reflection to occur. Okay? So the medium the wave is traveling in is what affects the speed of the wave. Okay? All right. So it is important to know the speed of a wave is dependent on the properties of the medium in which the wave is traveling. Right? Not just what medium, but also the properties of the medium. Things like air and water convey waves at different speeds depending on their temperature. Right? The speed of sound in air at 0 degrees Celsius is 330 meters per second. Raise the temperature to 20 degrees and it's 343. Okay? The hotter the air, faster the wave travels through. Okay, the sound wave anyway. Right? And it's the same for any fluid. Okay? Waves travel through fluids at different speeds based on their temperatures. All right, everybody okay with that? All right, so this was just another diagram of that video we had yesterday. As the depth decreases, okay, the waves got taller because out here in the deep water, they were very long, but as they got towards the shore, their wavelength decreased considerably, and that caused their wave height to increase because, of course, we have to conserve the energy of the wave. If it slows down, okay, it's got to get taller, right, and conserve all of that mechanical energy. Questions on that? That's the weird thing about earthquakes, is there are actually different kinds of waves, right? They travel at different speeds, okay? And so as a result, you can detect that like aftershocks, okay, are things that are caused by like these reflected waves that have actually traveled, bounced off the other side and come back, okay? Stuff like that. So as long as we understand that kind of stuff there about the waves and what kind of affects them, okay? That's what's important for today. All right. So when you're dealing with waves, okay, if we want to calculate their speed, the best thing to do is to use the properties of the wave. That would be its wavelength, its period, or its wavelength and its frequency, rather than trying to time a wave over a distance. Okay? The reason we try not to do that is a wave is not like an object. It's a lot of times very difficult to determine, all right, when did the wave pass that point? When did the wave pass the next point? Because a wave is fluid. Okay? It's hard to kind of tell where it starts and where it ends very easily, like an object that would physically pass a finish line. Right? So we try not to do distance and time for waves. We still can, okay? Especially if it's a sound wave. Okay? A sound wave is fairly easy to do the distance and time thing with, because you can, once you detect it with your ears, you can stop the timer. Stuff like that. Does everyone kind of follow me there? So yeah, I don't know if anyone's ever noticed this, maybe when you were younger and you had like track meets at school, okay, sometimes if you were far away from the starter, okay, the pistol would fire, you'd see the smoke, and then it was a second later before you heard the sound of the shot, okay, and that's because sound travels obviously much slower than light does. We see the flash, the muzzle flash and the smoke, but the sound takes longer to get there because it doesn't travel as fast. That's important if you're timing the race. If you're using hand timers to time the race, they have to watch for the smoke. If they wait to start the timer till they hear the sound, people are breaking records left, right, and center, okay, because they're starting the timer a second late in a lot of cases. All right. So everyone good with the formula? V equals lambda over t, and because t equals 1 over f and f equals 1 over t, it can also be written lambda times f, which is the form you see it written in more often and on your formula sheet. Both forms of this formula are not on your formula sheet because it's expected that you know this, and this is on your formula sheet. All right. Questions there? All right, so a very simple example, and this would be like the absolute simplest question you would ever get, okay, probably in the whole course. You've got a sound wave, and you know the frequency of the sound wave is 262 hertz. You know the wavelength is 1.29 meters, and you're trying to find the velocity or speed of the wave. Okay, you just plug in your numbers here. V equals lambda times f. So we take our wavelength, 1.29 meters, multiply by the frequency, 262 hertz, and we find that the speed of that sound wave is 338 meters per second. So using that formula is, again, not something that's going to test your mathematical prowess, okay? Not going to have any trouble using this formula. It's the context of some of the questions that can get tricky. Anybody need that one anymore? Okay. All right, try that one. It's super easy. Just looking for a wavelength. Okay, I'll give you like a minute to do that. Okay, so for this one here, they give us the frequency, 2.0 hertz, and they tell us the speed, 5.40 meters per second. We're looking for lambda. Okay, so V equals F times lambda. If we want to get lambda by itself, we divide both sides by F. Right, so lambda will equal 5.40 divided by 2, which should give us 2.7 meters for the length of the wave. nothing too terribly difficult. Okay. Very rarely are you going to get a universal wave equation that only involves using the universal wave equation. Okay. Most of the time it's going to involve some other concept like V equals d over t, okay, or when we get to standing waves, some information about standing waves and wavelength and stuff like that. Okay. All right. I want you guys to try number 2 and number 3. Okay? 'Cause these are 2 examples of contextually tricky questions. All right, so I'm going to give you a few minutes on 2 and 3. Read them carefully, okay, and think about the context in which these things are happening. So number 2 is a 2-part question. Right? We're trying to figure out how far away the rock face is. So we're trying to find the distance the waves travel from the submarine to the rock face. Right? They tell us the sound has a frequency of 325 hertz. Okay? If you've ever heard submarines, they use like a pinging sound to detect stuff. Okay? The sound wave bounces off an underwater rock face and returns to the submarine in 8.5 seconds. They want me to find the distance to the rock face. How far did the sound travel in 8.5 seconds? There and back. This is an echo question. You always have to be mindful of echo questions because they tend to give you the time for the echo to return, which is twice as long as you need to detect how far away the reflective surface, in this case the rock face, is. So what do I need to do with that number? I need to cut it in half, right? Okay, so my time is going to be 4.25 seconds. That's the contextually tricky part of this question, is understanding that an echo travels there and back. Okay? All right. If the wavelength of the sound is 4.71 meters, okay, how far away is the rock face? All right. I've got the time, but if I want to find D, what else do I need? V. All right. So I'm looking for V, and I have enough information to find it because I have F and lambda. All right, so V equals F times lambda, which will be 325 times 4.71. It's like 1,530 meters per second.
Yeah.
All right, so 325 times 4.71. Okay, 1,530.75. So now I've got my speed. Now I can calculate distance by going V times t. All right, so that'll be my 1,530.75 times 4.25 seconds, the time it takes to get to the rock face, not there and back, and that will tell me how far away the rock face is. All right, so the rock face is 6.51 times 10 to the 3 meters away. All right, that's how all echo questions work. Okay? Echo questions either ask you to find how far away the cliff or rock face or whatever it is away, or they ask you how long it'll take the echo to get there and back and give you the distance to the rock face. Either way, you have to remember that an echo has to travel there and back. All right. Do we still need a little more time for number 3? Okay. Okay, let's have a look at number 3. So, fisherman anchors his dinghy in a lake 250 meters from the shore. So they're telling us how far the waves are going to travel. Okay, the dinghy rises and falls. So that's one complete cycle, right? So it's 8 waves that go by every minute. So the frequency is 8 waves per minute. Okay? Rather than hertz, which is per second, they gave us per minute, which is fine because they also told us how many minutes it takes for the waves to get from the shore to the dinghy. Right? So we can leave everything in minutes. So the time is 3.00 minutes. Okay, so I want to figure out the wavelength. How far apart are the wave crests? Remember yesterday we said that the distance between any 2 equal points on a wave is the wavelength. So they're asking us for the wavelength in a really convoluted way. All right, if I'm going to find wavelength, I'm going to need V and I'm going to need F. I already have F, but I don't have V. So I'm going to have to use V equals D over T. 250 meters divided by 3 minutes will give me how many meters per minute, which is fine. I can use meters per minute. 250 divided by 3. All right, gives us 83.3 meters per minute. So now that I have V, now I can divide by F, and I'll get lambda. All right, so F was 8, so we'll take that number and divide by 8. I'm going to get 10 meters. We only have 2 significant digits there. Okay, so 10 meters is the wavelength of those waves. Okay. Everybody with me on that one? So that one's kind of a wording trick. It's that distance between the crests, and we have to remember the definition of wavelength is the distance between any 2 equal points on a wave. The other thing was rises and falls 8 times. Right. Well, a rise and a fall is 1 complete cycle, so they were giving us the true frequency. Here's where this can get tricky. Okay, a question tells me that a person is out in the ocean and they count 5 wave crests going by. How many waves is that? Everybody wants to say 5. They just feel in their heart like 5 crests is 5 waves. 4. 5 crests is 4 complete cycles of the wave. Remember, they counted crests. That means they started counting here. That's 1 complete cycle. That's 2 complete cycles. 3 complete cycles. 4 complete cycles. It's 5 crests, 5 troughs, but it's only 4 waves. Because a wave is all the way up and all the way back to that point. Okay? That's another contextual trick that comes up all the time with universal wave equation questions. They tell you that the person counts the number of troughs or the number of crests, and you have to remember that the number of crests or troughs is 1 more than the number of true cycles of the wave. Everybody with me on that one? So that's just the last kind of contextual trick that you have to be aware of. Okay? All right. I would like you guys to try 5 and 6 here. I'll make them a little bit bigger, okay? But 5 and 6, because they require you to remember something about a certain wave property that doesn't change. Okay, so obviously number 5 is pretty straightforward. Just looking for frequency using the universal wave equation. So it's just V over lambda. Okay, you don't have to do anything else with that. It's just 1500 divided by 1.25. Okay, but for number 6, there's the trick is we have to remember that what doesn't change about a wave ever? It's frequency. So in the first situation, I know that the speed of the waves is 1500 meters per second, and their wavelength is 2.0 meters. In the second situation, they're in warmer water. Okay, and in the warmer water, they travel faster. They want to know what's the wavelength in the warmer water. All right, well, as long as I remember that the frequency of a wave doesn't change once it's produced, I can say that F1 equals F2, because that frequency doesn't change. And then I can just say that V1 over lambda 1 equals V2 over lambda 2. Okay. Those two things are equal. So, a simpler way to do this would be solve for F here, and then plug it in here, because I know they're the same number. Okay. And so what we'd be looking, sorry, this is supposed to be 1550 here. So when we do that, we're going to take our 1500 okay, and divided by 2, which is 750. I can't believe I almost typed that into the calculator. Okay, 750 meters, okay, would be our, obviously 750 equals 750. Okay, and now I just need to solve for what lambda is. Okay, so V equals F times lambda, so V over F, okay, will give me lambda. I take my 1500 and 50, and I divide it by that frequency, by 750, right? And now my wavelength is slightly longer. Everybody all right with that? So it's not a mathematically difficult question, but it does require you to remember that the frequency of a wave doesn't change. Okay? And so the frequency in the cold water and the frequency in the warm water are the same. Okay. All right. Okay, so I'm going to put up the universal wave equation questions from your digital workbook. That's what I want you working on. They're not going to take you very long because they're fairly straightforward, but that's what we got on our plate for today. Okay, so they're going to start about halfway down page 3, okay, and they go on to page 4, right? They get a little bit more difficult as we go along, but there's 2 things I still need to tell you about, and I just about forgot to do that. Okay, first off, if a question gives you information that is talking about sound waves, and it gives you a temperature, right? It's giving you the ability to calculate the speed of the sound in that temperature of air. On your formula sheet is this formula, V equals 332 plus 0.6 times temperature. Okay, the speed of sound increases by 0.6 meters per second for every degree Celsius the temperature changes by. Okay, 332 is the speed of sound at 0 degrees Celsius, and so this formula will work if you're ever running into a question about sound and they give you temperature for some reason. They're expecting you to use that formula.
Does it matter if you use Celsius or like Kelvin? Will they
it does, okay, because if you're using Kelvin, right, you're not using, you're using a huge number. If we're talking about temperatures we would survive at. Okay, and so this formula won't work because you're going 0.6 times 273 instead of 0.6 times 1. Right? So yeah, it makes a big difference. So don't use Kelvin, use this. And this works even for freezing temperatures, because if T is a negative number, then the speed gets smaller because I'd be adding a negative. So it's set up to use Celsius. That's a good question. Okay, the other thing, if a question is talking about radio waves or light waves or anything like that, it may not give you the speed because it doesn't have to. Radio waves and light waves travel at very fast. What's very fast? The speed of? I'll say it again. Radio waves and light waves. Speed of light. Ah, something that's on your formula sheet. 3.00 times 10 to the 8 meters per second is under other useful constants. That is the speed of light. So if a question is talking about light waves, electromagnetic waves, light waves, radio waves, microwaves, whatever, those are all light. They all travel at 3.0 times 10 to the 8 meters per second. Right? Last thing, 1 or 2 questions give you the frequency of some of the light waves, but they give it to you in megahertz. Mega means 1 million. So if it's 8.5 megahertz, okay, it is 8.5 million hertz. Right? Similarly, they may give you the wavelength, okay, in micrometers. Remember, a micrometer is 10 to the minus 6 meters. Okay, so keep that in mind in case that comes up as well. Okay. All right. You may. Okay, so you guys can get started on those. Obviously, you can access them on your phone as well if you get past where the screen is at.